So I want to dig in a little deeper to what we started. I kind of rushed through this last class, building up our approach to molecules, which is this LCAL method, this linear combination of atomic orbitals, And in some ways, this is kind of just kind of at a qualitative, kind of basic sense, this is exactly the way you would want to build a molecule. So you have, just like we build atoms by adding electrons together. Right? We thought every one electron atom is like a hydrogen, so multi-electron atoms are like sums of hydrogens. And naturally, we're going to want to represent molecules as sums of atoms. Right? And that's kind of how our math's going to work. Now, we haven't gotten to the point where I can write down a series of equations that allow us to calculate a property or a wave function of any molecule we want, any combination of atoms we put together. Doesn't mean that it's actually a molecule, but here I'm defining a molecule not in the sense that it might not be bound. We could certainly come up with combinations of atoms that we can use this method to calculate, but it doesn't give bonds. It just gives combinations of atoms put together. So the question of what makes a real molecule is a different question altogether. And we'll talk about that a bit more as we get to it. What makes a molecule a true molecule in terms of quantum mechanics. But we have the very simple idea. We think of molecules as collection of atoms, right? So the idea is that each atom, here I write an atom sub n, n molecule, n. Let's say there are n atoms in the molecule, and each atom has m electrons, some number m. The idea is we're going to represent each atom's wave function as a sum of m hydrogen orbitals, at least m. So if there are m electrons, then the wave function for our atom at the very least is a sum of m hydrogen wave functions, which I write phi here, these hydrogen orbitals. It could be 1s's and 2s's and 2p's, whatever you want to do. It's totally arbitrary. Right? At the very least, we're going to want to represent each electron with its own wave function, right? And then sum over them to construct our atom. All right. Again, remember the really powerful thing about quantum mechanics, more so than any other physical theory, is that it's linear. If something works for one thing, we can add those things together, and it will also work for the sum. All right? That's what we mean by linear. So if we know we have a solution that works for hydrogen, then we can also develop a solution for a problem that we can represent as multiple hydrogens added together. Right? That's how we're going to tackle atoms. We can look a little more carefully as we go through it how we actually do this in practice, but the idea is very simple. We're going to take some function we know and represent something we don't know by summing over a series of things we know. Hydrogen orbitals, hydrogen wave functions. And then to construct the atom, or construct the molecule, we're going to take each atom, wave function, and our wave function for our molecule will be a sum over all the atom wave functions. Okay, so we construct a wave function for each atom of things we know, and then we construct a molecule with those atoms, which are then constructed by things we know. So we can calculate our guess for the wave function of the molecule by just summing over, doing a double sum over all the electrons. Right? All a molecule is a series of atoms, which are a series of electrons. All right? So if every atom in the molecule has m electrons, of course some have different ones. Hydrogen only has one, but they all have m electrons. Then our molecular wave function at minimum is going to be size n times m. N times m, number of atoms times the number of electrons per atom. So we could have if we have 100 electrons, this can be a really, really big function. But there's nothing to stop us from doing that. It's totally allowed for us to just add things together like this. And I kind of glanced through this. We'll look at this a little more carefully. But when you write your wave function like this, where you're summing over electrons, in the end, all a wave molecule is just a bunch of electrons around nuclei. That's what this is saying. Schrodinger equation becomes a matrix equation, where it looks like H psi equals E psi, but we have these what we call matrix elements, H and S, which are equal to the expectation value of the energy, where I and J are some index, some electron. Right? So let me give you an example. For hydrogen, we have 2 electrons, 1 per atom. So the way that we constructed H2 was to say that, right, the electron, the wave function for the first electron, which we'll call, I guess, 1, R, is the wave function for the 1s orbital, centered at R1. That's the position of electron 1. Just the 1s orbital, it's e to the minus R. And then for the other electron in the molecule, R2, electron 2, we do the same thing, but now it's centered at R2, atom number 2. And that means that our wave function for our molecule, we're going to write as the sum of these. I'll just say approximately equal to, of course there's a number. Let's just say C1 times theta 1, phi 1 plus C2, phi 2. Right, so the idea is that a hydrogen molecule, in this view, is two 1s orbitals added together. Okay, so let's look at this expression here and see if we can calculate something for H2, or at least write it down. Each of these indices on this is the row and the column of the matrix, each of these correspond to the atoms, the atomic wave functions, right? In this case, our atomic wave functions are just electron wave functions. There's one electron per atom, so we don't have to do that first sum. Basically, that's a sum of one term. So this is, so when I calculate, for instance, the term H11, that's going to be the integral of phi 1's conjugate, that's the real, so I can just get rid of that, times the Hamiltonian times phi 1 again, d, whatever the integration is. Let's just do dr. Okay. And this is just, if we evaluate the Hamiltonian on this, we know that right, these are Schrodinger, these are wave functions for the 1s orbital, which is the end. So what you get out is the energy of the 1s orbital times the wave function by the Schrodinger equation. So this should give me the integral of phi times a number, E1s, times that wave function back. Get rid of these. And I can factor that out. That's just a number. And I'm left with the integral of phi squared. Phi 1 squared d tau. And that's 1. By normalization, this is 1, right? Because the 1s orbitals, remember the hydrogen wave function is orthogonal. If you integrate the square of 1, you get 1. And if you integrate 2 together, you get 0. So this is just E1s. Right, so it's just the energy of the electron in the 1s orbital. It's not too hard to show that H22 is exactly the same. All I'm doing is I'm moving my calculation from atom 1 to atom 2, but they're equivalent atoms. They're both hydrogen 1s's, so you get the same result again. And then we have this very interesting term, these off-diagonal terms, where you're integrating psi 1 times psi 2. D tau. And you may naively think, let's apply the Hamiltonian here to 1, you get E1s back, the energy of the 1s orbital, times phi 1, phi 2. And you would think that this is equal to 0. Because of orthogonality, you're multiplying a wave function times another one. And you would think that would be 0, but in fact it's not 0. And the reason why is because these two wave functions, the two atoms or the two electrons, are in different positions. They don't have the same origin. Right? If I draw a graph, for instance, here's atom 2, hydrogen 2, here's hydrogen 1. And if we look at the wave functions or the probability distributions for the two atoms or the two electrons, phi electron 1 looks like this. And electron 2, I'll just draw it in red, looks like this. All right, so what this is calculating is the integral, the area under the curve of the product. So what does the product look like? I'll just multiply these together. Well, it's going to be 0 where one is large and the other one is close to 0. So in this region, right, the purple line is basically 0, and you're multiplying by a larger number, that's 0. And over here you get 0. So the only place you don't get 0 is in the middle, where you have both of them kind of not very, they're both small, but they're both not 0. So the product wave function, psi 1, psi 2, again, doesn't have a lot of amplitude, but it's got a little bit, and it's in the center. Right, that's what's left. Right, of course, as those atoms come together, you have the larger amplitude region starting to overlap with the other larger amplitude region, and so as the atoms come together, this overlap becomes larger, but it's not perfect. Right, and so this means that this number, H12, is going to be less than 1. It can't be 1. The only time it can be 1 is if the atoms are on top of each other. Right? That's where this wave function would be overlapping this one, or 2 is on 1. And of course, that's impossible by repulsion. You can't put 2 protons in the same place. But it's got to be greater than 0. Greater than or equal to 0. Now, it could be 0. The way it would be 0 is if the two atoms are so far apart that they have no amplitude sharing, right? They don't share any probability of being in the same place. They're super far away, that would mean no bonding. Right? So they have to be, these off-diagonal numbers have to be somewhere between 1 and 0. And so the way that this looks then is our Hamiltonian looks like a matrix of these integrals, H11, H12, H21, H22. And then the way that I represent my wave, if the Hamiltonian is a matrix, then my wave function has to be a vector for this math to work. And what we're going to write as our coefficients for our vector are the coefficients on the outside of the sum. So each wave function has a weight associated with it. The sum of the squares of the weights equal 1. So what these weights tell you is how much proportion of the molecular wave function is in one atom or another. Okay, so if they're equal, so in this case here, C1 and C2, if they were equal, then the molecular wave function is an equal weight between hydrogen 1 and hydrogen 2. Right? But the wave functions don't change. Right? The wave functions are constant. Right? The only things that are really going to change are the numbers on the outside. Right? We fix the wave functions, the form of the wave functions to look like the 1s. They're never going to change. So the dynamic variable in this equation, if you will, is the weight of the two, whether the system is weighted towards one atom or another, the relative proportion of these constants. So the way we're going to represent the molecule instead is to write it as a vector C1 and C2. Right? And the idea is you can think of it as a coordinate system. You have one coordinate psi 1 and one coordinate phi 2, they have the x and y, then your wave function is going to be some vector on this plane. Right? Maybe this one is 1 over the square root of 2, 1 over the square root of 2. Right? That would be the equal one. And in fact, that makes a 45-degree angle. You bisect the plane with that. Right? And that would be an equal balance between the two wave functions. If the system shares probability between both of the atoms equally, you can think of that vector as being a vector in this diagram. Right? In fact, this is the way quantum mechanics is constructed. It's that each wave function you can think of as a direction in a coordinate system, like x, y, and z. And any valid system in this direct coordinate system is a wave function. So I can have a wave function that looks like this. I can have one that looks like this. I can have one that looks like this. I can have one that looks like this. I can have any of those. I span a circle in this direction. Right? And so I'm just representing my wave function as a vector in this space where my atoms effectively form the coordinate system. Right? We have a very specific term for this. the atomic orbitals, phi 1 and phi 2, which are 1s orbitals, are called a basis set. So much of chemistry, computational chemistry and theoretical chemistry, is about choosing how do we represent our atoms or our electrons, how to choose a basis set. This is a general math term. If you think about vectors in 3D space, so here's our vector v in 3D space, and let's say it lands on point x, y, and z. Let's give it a different one, a, b, and c. How about that? That'll be a little bit easier. The way we write this vector in component form is a times the unit vector x plus b times the unit vector y plus c times the unit vector z. Right, where x is the vector 1, 0, 0, y is the vector 0, 1, 0, and z hat is the unit vector along the z-axis. So I can draw that. Let me draw it with a different color. So this is z hat. This is c times z hat. This is a times x hat. And this is b times y hat. Okay, so again, the way we construct vectors in 3D space is multiply our unit vectors on the coordinate axes by the scalars that give you the length of the vector in direction you want. And we say, and they don't use this term, but they do in linear algebra, that the set x, y, z form a basis set of vectors. Right? I can construct any vector I want by taking linear combinations of x, y, and z. Right? Any vector in 3D space can be constructed with a linear combination of the basis set, x, y, and z. Okay? Quantum mechanics works exactly the same way. You have a system that has a basis set, in this case, of two basis vectors, psi 1 and psi 2. Phi 1 and phi 2 are two wave function atoms. And any wave function can be we can construct any wave function we want with a linear combination of those two. Right? And that puts us somewhere in this 2D plane. Right? So the idea of quantum mechanics is in fact just a theory of vectors. It's a linear algebra idea where what we're doing to solve the Schrodinger equation, all the Schrodinger equation is finding a set of orthogonal basis functions, a basis set, that satisfies all the properties that we want, that all of them are orthogonal to each other, and that it's normalized, and so on and so forth. Right? So we have some equation that defines the vectors that satisfy it, right? Our Hamiltonian or Schrodinger equation that tells us what kind of vectors are allowed. And what we ultimately are doing is solving this equation to find a set of vectors, a basis set of vectors that are orthogonal to each other at 90 degrees, just like x, y, and z. X, y, and z are orthogonal vectors. They're all at 90 degrees. You take their dot product at 0. And in quantum mechanics, it's the same idea. Your solution is a basis set of vectors that are orthogonal, and any solution of your system is a linear combination of them, right? So the only difference is that when we talk about space, vectors in space, we only have 3 dimensions, right? If we're in time, if we deal with time, then we have 4, right? But that's the most you're ever going to deal with in physics, right? 4-dimensional vectors, x, y, z, and t. But in quantum mechanics, so for instance, the hydrogen atom, just a bare hydrogen atom's basis set is infinite in size. Right? You can have the 1s, right? You have a basis set of the 1s, the 2s, the 2p's, there are 3 of them. the 3s, the 3ds. There are 5 of them, 4s, and so on and so forth. It goes on forever. So quantum mechanics in some ways is equivalent to, there's some up to a certain limit. Quantum mechanics is the math of vectors in an infinite dimensional space. That's why we don't tend not to teach it this way initially, because that's kind of a hard thing to put your head around, right? The idea of having a vector that has infinite components, all right? Now we can't do any math with that. It's hard to deal with infinities. But when we make these guesses like we do, well, we can truncate our basis set to something small, right? Here I just truncated it to 2, right? And so now we have a system that is defined in a 2-dimensional plane, and our molecule can be any combination of psi 1 and psi 2, right? Remember that there's one caveat, and this is the big difference between space vectors, if you will, position vectors in quantum mechanics. And this is the key point. And so let me draw this plot one more time. Phi 1 and phi 2. Right? Any molecule or any system is satisfied by some vector in this space. And again, it's 2 dimensions, so it actually goes like this. It could be in any direction. You have a negative coefficient. So let's draw this one right here. Let's say this is 1 over the square root of 2, 1 over the square root of 2, and this is 45 degrees. All right, the important thing is that they form a circle. So here's another solution to this equation, the Schrodinger equation for this system. Here's another one, here's another one, here's another one, and here's another one. And the radius of this circle, so the length of these vectors, is 1. It has to be, because remember the system is normalized. If you take the square and integrate the square, you get 1 back, right? It's probabilistic. So quantum mechanics, or wave functions, let's say wave functions, are vectors, and in a finite or infinite dimensional space, or you could say they're of finite or infinite length, whichever way you want to think about it, or length in terms of the length of the vector, the number of coefficients, with length 1. Right? That's normalization. That's all normalization means, is that the vectors that can only exist are ones where the squares of the components sum to 1. All right, so in some ways, this idea of a sphere or a circle is deeply embedded in the structure of quantum mechanics, because every solution of the Schrodinger equation for a given basis set forms either a sphere of some dimension, or the dimension's the number of functions in the basis set. If we had 3 wave functions we added together, of course this would look like a sphere. If we had 4 basis functions for our system, if we had 1s, 2s, 2p's, or something like that, then it would be a 4-dimensional sphere, or 5 or 6, or infinite dimensional, if we had an infinite list of basis functions. All right, so it's not surprising, and maybe it's not so surprising that we don't teach it this way in undergrad, because again, it really focuses on a very fundamental aspect of algebra to represent a system this way. That's why we do things with integrals typically. But there's something really powerful and elegant about this construction, right? And it describes, I think, very beautifully the kind of requirements that you need for a solution or to any quantum mechanical system, that it can always be represented as a vector in some space with length 1. Right? Every possible system. All right, it's just about how you construct that space. Choose the basis set that you choose, the constraints you have on the basis functions, which is the Hamiltonian, things like that. All right, those are the things that ultimately define the system, but every quantum mechanical system is effectively the same. Its solutions form a sphere or a circle in whatever space set it exists in. Okay, so again, this is why I always bring up vectors and matrices and stuff, because the math works beautifully for that. Okay, so anyway, I digress. Back to this matrix H. So again, this is our Hamiltonian, right? And it's really just a guess. Again, for the hydrogen atom, the true solution to the wave function of the hydrogen atom is not this. It's not just adding two 1s orbitals together. It's just too simple. There's good reason it's too simple. It doesn't actually, it's not a true answer, but it's a good guess. Right? It's what we would call a minimal guess. Right? So the simplest guess we can make for what hydrogen looks like in terms of its atoms is just to add two 1s orbitals together. Right? So we call this, this is the minimal basis. And one of the things is that what we're doing here ultimately with this matrix, this Hamiltonian matrix, is that we're guessing the energy of the system with our guess function. Right? We're not actually solving the exact Schrodinger equation for H2. We're making a guess for what we think it looks like, and then calculating the energies of the system with that guess. Right? It's just like that problem 3 on the midterm, where I had you guys attempt to calculate the energy of the hydrogen atom with a guess wave function. Right? Here we're doing the same thing. We're making a guess, and we're guessing what the energy is. Right? Okay, so that's this Hamiltonian. That's the Hamiltonian. In this case, it's how many basis functions you have, but you can think of the columns and the rows of this as being phi 1 and phi 2. All right, and then we're left with another matrix on the other side of the equation, S. But S is just the overlap of the wave functions, right? We've talked about this already. So S is also a function, or a matrix, S11, S12, S21, S22. And S11 is going to be the integral of phi 1 d tau, which is 1 by definition. Right, so this is easy enough. These two are the same. Of course, it's the same as S22. Maybe I write 1's there if we want. And S12 and S21 is the integral of the product of the wave function. So we looked at that. We said that they're kind of far apart. There's some overlap that's shared between them, but not complete. So S12, which is the same as S21, is going to be greater than 0, greater than or equal to 0, and less than 1. Okay? And it's up to the computer, it's up to the way that we construct the molecule, what value this takes. Okay? The closer the orbitals are, the more overlap you have, the further they are, the less overlap they have. All right? So it's just a function of the distance that you choose between the two atoms. Questions? Okay, let's break down. Let's now talk a little more about what happens when we solve this equation. All right, when we will actually work out some problems later on where we'll go and solve this Schrodinger equation for the energies. All right, but let's not do that today. Instead, let's just kind of talk about the results a little bit. All right, we'll work on the math later. So the math's a little complicated. But we'll do an approximation called Huckel theory later on that will allow us to calculate these Hamiltonians really, really easily. It'll be really fast. You can do it in Wolfram alpha. Okay, so the important thing, well, let me just write this matrix down one more time just to get a sense of what we expect from this. I'm going to write the whole thing out. We have this matrix and the time C1 and C2. That's our wave function. It's equal to the energies of the system times S11, S12, S21, S22. This is our overlap times the wave function. This is just the Schrodinger equation. What we want to do is we want to solve this. So there's a couple ways to solve this. One is to take h minus es times the wave function and set it equal to 0. This is a algebraic equation that you can solve. And in fact, for hydrogen, it's a set of two algebraic equations to solve a system of equations. All right, so we can use algebra to solve that. The other way is to change our basis set from phi 1, phi 2 to something new such that h12 prime, which is the h12 in the new coordinate system, which is equal to h21 prime, is equal to 0. All right, so in this new basis set, we would have a number h11 prime, h22 prime, and then zeros on the off diagonals. And then we'd have some wave function c1, c2 equal the energies of the system times 1, 1, 0, 0, c1 prime, c2 prime. All right, so what we call this is diagonalization. Diagonalization. So what we're doing is we're taking a system that's represented by two separate atomic functions. So your basis set is phi 1 and phi 2, so initially your coordinate system, if you will. If we think about vectors, your coordinate system is phi 1 and phi 2, and here's your wave function. All right, and what we're going to do instead is rotate this system after diagonalization that now we have coordinates c1 phi 1 plus c2 phi 2 and c1 phi 1 minus c2 phi 2. And what happens is that this gets rotated like this, and now your wave function is now right here along the axis system. It's actually a vector along the axis. So what we've gone from is this is an atomic basis, right? Atomic coordinates, if you will, right? The coordinates of our vectors are the atomic wave functions, to a molecular basis, where our axes of our vectors, if you will, are linear combinations of the atomic numbers. Right? That's a very, very subtle point, and kind of hard to see. But it effectively means that we're rotating this coordinate system into a new orientation that makes it so that the new wave functions that come out of this system, phi and phi prime, are orthogonal to each other, like that. Right? This is, in fact, is how we solve the Schrodinger equation in general. We set up a problem, and we diagonalize the Hamiltonian to form a new basis that's orthogonal. And that's how we create orthogonal wave functions, is doing this diagonalization process. Okay, you can do this very easily in Wolfram alpha. It's not hard. So when we get to calculating some things more quantitatively, I'll show you how to do it. It's really easy. Right? Any computer can take a square matrix and diagonalize it with ease. In fact, it's one of the things that computer scientists are really good at. They've spent a lot of time. This process, actually, of taking this equation and then calculating it with a new coordinate system that causes it to be diagonal. This is something that computer games, video games, do millions of times, hundreds and thousands of times a second. Right? Anytime you're calculating light paths or physics of motion, or you're doing machine learning, you're doing this process over and over and over again. Right? So there's really efficient ways to do it on the computer. The cool thing about quantum mechanics is that no matter what you choose, No matter what system of atoms, how you sum the atoms together, what kind of weird wave function guesses you make, it doesn't matter. This is always diagonalizable. Always generates a solution. Might not be a right solution. It might not lead to a real molecule. But you can always diagonalize this system. Right? It's one of the benefits, one of the things that we haven't really talked about this too much, but one of the postulates is this idea of orthonormality. Because we assume orthonormality, the wave functions are orthogonal and they're normalized, the only way that can happen is that if every solution, everything that we set up can be diagonalizable. So if you build a Hamiltonian that can't be diagonalized, you can't solve it in this form, then it's not a real Hamiltonian. Right? It does not represent a physical system. So this process is guaranteed for any physical system. Right? It'll never fail. It might not give you a reasonable answer, but you can do it, which is really powerful. That says that we're never going to have to worry about the physics failing us. Our guess might fail us. We might make not really a physical guess of what our system should be represented as. Maybe 2 1s orbitals is not a good way to represent hydrogen. But we know that the math will always work out. That this process is always guaranteed. Right? It will always work. And if it doesn't, then it's not real. It's not a physical system. We're guaranteed that. So that's really nice. That means we can make whatever guess we want and check it, see if it works. If it doesn't, then we'll try a new one. Okay, so let's see what happens now. So what I'm doing now is diagonalizing this matrix system. So now I have some new set of wave functions. And there's going to be two, in this case, there's going to be two possible energies, a plus and a minus one. So this generates, this process for H2 generates two new wave functions, two new molecular orbitals. We'll call them molecular orbitals. Let me grab the, yeah, here it is. So the wave function of our molecule, we get two new wave functions out, a plus and a minus combination. So the normalization constant is 2 plus 1 plus or minus s, where s is the overlap between wave function 1 and wave function 2. We'll just call that S12 because that's to keep it consistent. Of phi 1 plus or minus phi 2. Right, hydrogen 1s orbitals. There's a plus and a minus. Okay, so qualitatively what happens? So let's put hydrogen number 2 here, hydrogen number 1 here, and let's put the energy of the 1s orbital right here. So our atomic basis, before we do any diagonalization, when we have the two atoms far apart, the energies of the two electrons are at this energy. Right? We have two 1s electrons floating around. And then what we're going to do is we're going to bring those atoms together. They're going to start to overlap. And as they start to overlap, we're going to start to get combinations that look like this combination of two 1s's and the difference. And the energy splits. So when hydrogen reaches its equilibrium bond distance, let's do it like this. Let's bring it like, yeah, let me do it like this. Like this, so when you bond the atoms together, so this is 1, 2, H2, the orbital energies become no longer degenerate and they split into a pair, where one's lower in energy than the reference energy, the 1s, and one's higher. So this is psi plus, which is 1s plus 1s. And this is psi minus on the top, which is 1s minus 1s. Like so. And then what happens is we have to put the electrons somewhere. So we have two unpaired electrons in our hydrogen atoms, and we bring it together to form a molecule in the middle. Those electrons will go to the lowest energy place by Hund's rule, so they end up in that orbital down there. Let's look at the structures of these wave functions. I think I kind of mentioned last class, but let me just, again, this is just a little bit of review. Maybe I didn't mention it. Maybe we're kind of caught up at this point. So psi plus is the 1s orbital plus the 1s orbital. All right, so 1s orbitals, again, are spheres. They're spherically symmetric. Okay, so I have two hydrogens that look like this. These are the 1s orbitals. They're spheres. And I'm going to bring them together and then add them together. Now, what happens when I add them together? Well, I'm going to get amplitude sharing where they're overlapping, and then that's going to deplete some of the amplitude from where they're not overlapping, so there's going to be some buildup of probability density or wave function in the middle. So when I add them together, I get something that looks like this. It's cylindrically symmetric. It has one phase the whole way. And here's our two atoms, 1 and 2. All right, so now the electrons are shared. Right, the electron density has been pushed away from the exterior. So again, in the original wave functions, they're spherically symmetric. So there's equal amount of electrons on this side as this side. But then when I add them together, that density gets shared between the two. And again, because probability is normalized, I get more in the center, which means I get less on the edges. Right, so the system kind of truncates in like that. Yeah. Right. So electrons are shared cooperatively between the orbitals, between the atoms. Right? Right? That's a good thing. Right? That's a positive thing. And we'll look at it a little more carefully. We can show that that lowers the energy of the system. Right? Which is why this orbital, the plus combination is lower in energy than the reference where the system started. Right? So we call these bonding orbitals. Ones that have this constructive overlap in the center. Right? This is a covalent bond. This is all covalence is. Is a cooperative sharing of electron density between two atoms. So we have a nice bonding orbital here. And then let's look at the other combination that we formed, the minus sign, which is psi 1s minus psi 1s. Maybe a better way to look at this is psi 1s plus the negative version of it. Like that. Maybe a good way to think about that is to write, so here's psi 1s for the one atom. Call this electron 1. And then here's the orbital, the negative, the subtract, the negative, the flip, the mirror image version, the opposite phase version of psi of 2. It's a different phase, so you can think about this as being positively valued and this is negatively valued. Well, no, that's not fair. Well, that's if you're adding them. Right? So you can either think of it that it's a reasonable way to think about it. And so when these start to overlap, think of these as sine waves. You have a sine wave or a hump that's positive, and you're adding to it a hump that's negative, and they cancel each other. Right? So what this leads to is destructive overlap. And so the area between the atoms gets depleted in intensity or probability. And the exteriors, the electrons exist on the outside of the bond, if you will, in this orbital. Right, so electrons are not shared cooperatively in this orbital. Okay? It's not too hard to show that this is an energy destabilizing effect. We call this an antibonding orbital. There is also what's called a non-bonding orbital. We haven't talked about those yet, but we'll see them soon enough this week. But every bonding orbital always comes with an associated antibonding orbital. All right, every time you create a bonding interaction, you also create another orbital that is the opposite. All right, so and it's counter they reinforce each other. The more this becomes bonding, the more electron density you share in the bonding orbital, the more energetically stable it becomes. Right, that's basically you're making the bond stronger. Then the corresponding antibonding orbital also becomes even more antibonding. Right? That's just conservation of energy, because what you're doing is you're starting with a system that is at its energy is at 2 times the E1s, and so that means that the total energy of the system once you bond has to be at E1s times 2. So the further this goes down, the more this one goes up. So if I had a really, really strong bonding interaction and it stabilizes it this much, then the antibonding orbital is going to be correspondingly taller as well, even more destabilized. Okay. So again, the important MO is that if you add n atomic orbitals into your mix, you import, let me write this, import n atomic orbitals into the Schrodinger equation, you export in molecular orbitals out. Right, that's just due to conservation of energy, right, and also due to the matrix size, right, as well. So in general, if you have a bonding interaction, you form a corresponding antibonding interaction as well, at higher energy, roughly equivalent higher energy, though there are exceptions. Okay, so what does that mean? Well, in the case of hydrogen, again, the electrons by Hund's rules want to go into the lowest energy orbital possible. So both the electrons fill the bonding orbital, and so we would expect H2, for instance, to be a stable molecule. Right? All of its electrons have bonding interactions with each other. None of them are in this antibonding system. So we would say that H2 has 2 bonding electrons and 0 antibonding. Right? And that makes me think that's a reasonable suggestion to say, okay, maybe it's stable. And in fact, we define something. Let me see if I can find a place to put this. Go ahead and erase this for now. We often define, here's our first chemical property we can define, called the bond order, which is basically single, double, triple. Right? We talk about single bonds, double bonds, triple bonds. That's the bond order. So whether single or triple, and that is defined as 1/2 times the number of bonding electrons minus the antibonding ones. Right? We'll use this number a lot. It's a really useful metric for us to determine stability. So in the case of H2, we have 2 electrons in the bonding MO and none in the antibonding MO. So for H2, we expect a bond order of 1. Right? It's got a single bond. Right? This means it's the same thing as it has a single bond. Okay? So just by looking at this, we can already predict what kind of bond it has. Right? It's got a fully filled bonding orbital, should be nice and stable. Nothing too exciting. Okay. Now let's think about what else can we do with this without even changing anything. All right, what can we look at something more complicated? Well, what about instead of H2, we remove an electron. Now we have H2 plus. All right, well, H2 plus has a bond order of 1/2. Right? So it kind of has a weak bond, but it has a bond. But obviously much weaker. Right. Now we could also ionize. We could also put an ion in H2, or an electron in H2. Oh, sorry, that's the wrong spin. I could put another one in here as well. Right? H2 minus. Well, this has a bonding orbital, a bond order of 1/2 as well, and we would predict it to be weak, have a weak bond, but a reasonable one as well. Also bonding, but weak. However, if we take H2 minus, this has a bond order of 0. Right? Now I have both orbitals filled. That means that I've put 2 electrons in the bonding orbitals, and they're completely canceled out by 2 electrons in the antibonding orbitals. Right? So this has no bond. And in fact, when you do this, H2 minus immediately dissociates into H minus plus H minus, right? Which has a fully filled valence shell. Those are really fairly stable anions when it comes to anions. This is spontaneous. Very fast process. When you take H2, double anion, put 2 electrons in it, it just falls apart immediately. Right? I don't have to do any calculations, right? All I have to do is, right, I don't even have to know how far this splits in energy, right? There's nothing quantitative about this graph. All I'm doing is I'm putting filling shells of electrons. I know that I'm going to form a bonding interaction, so I'm going to get a splitting like this. And just by throwing electrons in it, I can already tell you the electronic properties of hydrogen. Now here's a really interesting thing. Right? Again, I can do even more than that. Let's say, for instance, that I have regular old H2 here, and I excite the molecule with a little bit of energy. But what if I can calculate the energy difference between these two? What if I shine light at lambda, which is equal to that wavelength difference, the energy difference? Or I'm going to take one of these electrons and I'm going to promote it here. Right? So there's an excited state of electron as well. We'll call that H2 star. This has a bond order of 1/2. This is a bound molecule. Okay? So I can excite an electron internally within hydrogen and still keep it together. Now, because the bond order is 1/2, we would expect that H2 excited state is much weaker in terms of its bond strength as H2, because now you have an electron antibonding orbital. But there's nothing stopping it from existing. Okay? And then, in fact, that's very true. However, if I do that for H2 plus, now what I've done is I've taken the 1 electron that's bonding and I've put it in the antibonding orbital. H2 plus excited. That bond order has 1 antibonding electron and none of the bonding. It's actually minus 1/2. It doesn't even exist. So interestingly, just by drawing these 2 lines, just by drawing these lines and making these electron arguments, there's a really interesting thing, is that H2 has many, it turns out has many excited states, electronic excited states. And H2 plus has 1, has none. It only has a ground state. The moment you put any energy into hydrogen's electron and pump it to a higher level, H2 plus falls apart. Right? And that's why, because you've killed all that bonding. Right? There's no bond order left. You've moved the only bonding electron into an antibonding orbital, and there's no bond left, so it just falls apart. So H2 plus only has 1 electronic state, just its ground state. It cannot accept any UV photons, because that will just associate it instantaneously. There's nowhere else for that energy to go. But H2 has tons of electronic excited states, tons of them. It's very interesting how, it's actually really cool how diverse hydrogen's energy landscape is, because of the fact that no matter what you do, if you put a photon into hydrogen, it will always have one bonding electron left, no matter where you put that other electron. Okay. So for the last 10 minutes or so, I want to just do a little bit more deep dive into hydrogen. And then next class, we'll dig into more interesting molecules. We'll think about, we'll add a helium, right? We'll do helium next. We'll add a helium maybe, and then we'll go to the carbon, nitrogen, oxygen series and look more carefully there, right? Where we can start to do much more interesting things. All right, so what I want to do really quickly is just talk a little bit, one more time, maybe I should have done this earlier, but talk a little bit about this equation here, the structure of it for H2. I want to show you where bonding comes from. Why do we even have bonding? And so what I'm going to do is I'm going to look at H2 plus. Okay, so I'm going to use the same expansion I used for H2. Hydrogen 1s orbital on 1, hydrogen 1s orbital on 2. There's only one electron. So the electron-electron repulsion term goes away. Right, that's the hardest part of the whole process, is calculating the repulsion between two electrons, because they both move very quickly, and you have to keep track of all of them together. So by going to one electron, we get rid of that. And what you can show, if we draw, so for H2 plus, we have a electron here. And again, you form a bonding and anti-bonding pair of H2 plus as well. Nothing's changed. I'm going to call this energy difference between the two delta E. Right? So how much does that split as a function of the atom's position? You can show that the energy, okay. Well, let's do it like this instead. Instead of delta E, I apologize, let's call this E plus and this E minus, like that instead. We can calculate the difference. But what you can show is that it is equal to the energy of the 1s state plus a term proportional to the attraction or the repulsion of the two hydrogen nuclei. Okay, so R here is the bond length of the molecule. So this is how much the two protons repel each other, just a number. And then it's equal to this weird combination of numbers, J minus K over 1 plus S. I'll write what these are in just a second. And then here delta E is J plus 1 over R. R is the bond length. 1 plus or minus. Oh, let me rewrite this. Sorry. I apologize. Let me rewrite this. I have a better equation here. So it's E H1S, sorry. So let me do this again. Plus E squared over 4 pi epsilon naught R. That's the nuclear-nuclear repulsion. And then it's plus J plus 1 over R over 1 plus or minus S plus or minus K plus S over R over 1 plus S. I'll write what these J, K, and S's are in just a second, okay? So again, this is the atomic energy, right from the start. This is the repulsion of the nuclei, or the protons. And this is our electronic part, the electronic bonding, anti-bonding part. All right, and R here is the bond length of the system. Okay, it's just a number. All right, so we have three things I haven't defined: J, K, and S. S is the overlap. So S is the integral of phi 1, phi 2, which is d tau, which is S12. Okay. We call this the overlap integral. How much the wave functions overlap. J is a really interesting integral. It's the integral of 1 over the position of one of the nuclei times the wave function squared of the other nuclei. So this is how this is called the interaction. Integral, and it's how attracted the electron is to another atom, to the other atom. Okay, so the idea is that, I'll just draw it really here. The way H2 plus looks like is you have 2 protons, and let's say your electron is attached to 1, and J tells you how much these are interacting, right? The other electron, the other proton, right? So J measures this. This measurement right here, the energy between the proton and the electron is just H1s. E1s is just the energy of the 1s orbital, and J tells you how much energy of attraction there is between the other proton and that electron. And then K is called the exchange integral, and it's 1 over the position of one atom times the wave functions. Let me write phi, sorry, I apologize. I'm changing my notation here. This is R2 times phi 1 squared. And this is R2 or R1 times phi, the wave function at position 1 times the wave function at position 2 d tau. This is called the exchange integral. The reason why it's called the exchange integral is it tells you what the energy of taking this electron and basically swapping it over here and making it E2 instead. So let me write that down. S says the overlap between atom 1 and 2. J is the attraction between electron 1 and atom 2, or vice versa. And K is the energy of moving the electron from proton 1 to proton 2. We call that exchange. Another way to think of it, you can either think of it as, it's really in terms of the electron, how much energy it takes for the electron to be attached here and then move it here. Right? Because these are identical protons. And so there's nothing really affecting you to change this, but there is the integral is not 0. So there is some energy associated with taking this electron and putting it here or putting it back over there. Right? Basically, you're exchanging the protons. Right? So that's what the energy is dependent on. Right? So bonding, so the only thing that bonding really has anything to do with, this is not bonding, this is a repulsion between the atoms, the protons. This is just atom energy. So this part right here actually tells you something about the bonds. I'm missing a plus or minus, I think. No, I'm not. And what it says is that bonding has to do with how much an electron on one atom interacts with the other atom, and also how much does the orbitals or the atoms allow the electron to move from one atom to another. Right? So this kind of gives you a sense of how well they talk to each other, how willing they are to share the electron, K, and J tells you how strong that sharing is. Well, no, this shows you how strong the sharing is. This shows you how attracted it is to the atom itself. Okay, so this idea of exchange is essential in quantum mechanics, and it's the key to bonding. The fact that you're allowed to take an electron on one atom, localized on one atom, and move it to another atom, that causes bonding. And in fact, I can show it to you in just the last minute here. We can plot these. For H2+, you can actually calculate functions for all of these. I'll probably have a little homework set next problem to plot these and look at them. Next week. If you were to plot these, so if I were to plot R versus energy for each of these terms, what you would find is that J plus 1 over R, which is this term right here, is always repulsive. All right, so the interaction between proton 2 of electron 1 is attractive. You also have this 1 over R term that dampens it and ends up being positive the whole way through. That's not so surprising because you have a positive number here times a positive number here. Psi squared is always positive. The integral of it is positive, the interaction. All right, so in fact, the interaction causes the system to stretch a little bit further. You can think of that as kind of almost like, the closer you bring the atoms together, you've got more repulsions between the protons, and that's causing this to rise. But if you look at the other function, k plus s over r, there's actually a balance. So as the atoms get closer and closer together, this number gets huge because the atoms are touching. And if you an electron here, that electron is not easily shared between the two protons because the protons want to move apart. So at close distance, I'll get it with a different color, k plus s over r is quite high, but there's a region at which it becomes negative. And then it kind of goes to 0 as r goes to infinity. So this is k plus s over r. So there's this natural kind of Goldilocks zone right here where exchange of electron from proton 1 to proton 2 is energetically favorable. It actually lowers the energy. Okay? And again, you just think about it as the idea that a covalent bond is where two atoms, two nuclei, have a region where they can cooperatively share an electron. What does cooperatively mean? It means that when it does it, it lowers the energy, right? That there's some energetic impetus for it to share. So the energy is going to be negative if it has some impetus to do so. And so this idea that the system is allowed to move that electron from atom 1 to atom 2 at a certain distance and it's energetically favorable means that, well, that's just a covalent bond, right? You have some positive influence from the ability of moving an electron from atom 1 to atom 2. That's just sharing, right? So sharing is good here. And of course, sharing doesn't matter at long distance because it's a long distance, right? So there's no overlap. So here S goes to 0. There's no overlap, so there's no way to share at long distance. And then at close distance, sharing is bad due to repulsion. You can also think about it as that the electron, when you're really close together, you think about the electron is both simultaneously, the wave function of the electron is both simultaneously at near R1, the position of atom 1 and R2, and as R1 goes to R2, right, as the atoms start to come together, well then the electron, we'll call this position 1 and position 2. So as R1 goes to R2, as the atoms come closer, the electron exists in two states or positions simultaneously. that overlap. All right, so you have an electron that exists in two spaces, R1 and R2. You've brought R1 to be equal to R2. So now the electron coexists simultaneously in the same space of itself. So the electron repels itself. It's not really how it works, but and basically in this approach is that the idea is. Right, that this is a state that the electron can be in around atom 1. This is a state where the electron can be around atom 2. And then when you bring the two nuclei together, that both of those positions are the same, your wave function hasn't changed. It's still exchanging between those two positions, but now those positions are right on top of each other. And the only way that you can interpret that in terms of this math is that the electron is repelling itself. Right? Remember, electrons can't exist in the same place at the same time. Right? This is the Pauli exchange principle, or Pauli repulsion. That electrons can't exist in the same space at the same time. So if you build a wave function for your electron where it coexists in two spaces at the same time, and then bring those spaces closer and closer together, then what happens is the electron repels itself in that formalism. Right? The actual math of what the electron does is more complicated than that, because it's kind of hard to think about an electron repelling itself. That doesn't make any sense. But in fact, that's how the math works out, that the electron actually affects itself and raises its energy. So here you have electron self-repulsion and nuclear repulsion here. They start to both play a big role there. So the energy skyrockets as a function of temperature, or temperature position. So naturally the system wants to be at low as energy as possible, and that's going to be right here where sharing's good. Okay? When you add all these terms together, when you add everything together, add it all up, you get a potential surface, a potential energy that looks like this. Right? Add it all up. Right? And this is just the Morse potential. Right? We've seen this before, right? With vibrations. Okay. So again, the idea actually, so this is the important part, and I'm surprised I got to this point already. And we'll talk more about it next class, is that what is a molecule? Well, a molecule can be any combination of atoms and electrons. Right? Doesn't matter. But what do we know as a molecule? Well, we know a molecule is something that is bound, in that you have atoms that are attached together and there's some amount of energy to pull them apart. And the idea is that the existence of a molecule, what makes a molecule different than a collection of atoms or a collection of electrons, is that when you combine them together, you form a state at some position that has less energy than when you add them all together. Right? There's bonding, there's sharing. Right? So a stable molecule, right? Stability. A stable molecule is one that forms an energetic minimum at a finite distance or a finite displacement for its electrons. Right? So if you form, once you add all the integrals up and your energy as a function of the bond length, looks like this, where it goes to negative, stabilizing, and you have this minimum form like this, that's a stable molecule. Right? That's what stability really means. That's what we mean by stability. Now, there are different types of stability, right? I can show you a bunch of molecules that you'll look at and be like, there's no way that's actually stable from like an organic chemistry perspective. But I can show you that they're bound. They have vibrational levels in here. Right? There are vibrations. It's a real bona fide molecule. But you would look at that molecule that I wrote down and be like, there's no way that's stable. Right? So there's different levels of stability, right? Stability is a relative term. But if I were to make an absolute argument for what is stability in chemistry, a stable molecule is one that forms a minimum, an energetic minimum at some position, and is such that it allows it to form, bound vibrational states where the molecule can exist and vibrate freely without dissociating. Okay? There are very different levels of stability, of course. Right? We'll see that in this coming week. Different levels of stability. But there is one absolute stability, which is, does it form a minimum or not? That's it. Right? And H2 is our simplest case. We don't even have 2 electrons. We're just sharing 1 electron between 2 atoms, 2 protons. That's all H2 plus is, and that's all we need to form a bond. We have 2 protons, 2 atoms sharing electron density together equally. And that's enough to get you a stable bond. H2 plus is a stable molecule. 100% stable. It's not stable in room temperature. If you collides with anything, it's going to fall apart. If you shine the sun at it, it's going to fall apart. But it's still a stable molecule. Right? It still exists. It's a real molecule. It has a real bond energy. It has vibrational levels. And it has an electron in a bonding orbital. Those are all the claims of a molecule. Right? So I'm hopefully by the end of the semester that I'll expand your mind on what you believe is stable or not. All right? We'll start looking at even weirder molecules starting next class, as well as some more normal ones as well. Right? And we'll use this, we won't do so much of this math anymore, right? We'll go back to this idea of adding orbitals and doing these qualitative diagrams and using geometry and a little bit of intuition to come up with these molecular orbital diagrams, instead of having to do all this math. Okay? All right, guys, have a good one. Last week of labs. Yeah, have a good one.
Thank you.
Thank you.